of the semi-major axis are related by a constant of proportionality. Now, I can always find a number such that p squared is k times a cubed. Just divide p squared by a cubed. The point is that if you divide p squared by a cubed for each of the 5 planets that Kepler knows about, you get the same answer. And this is very important because this is then not a property of the planet, it's somehow a property of the solar system. There is something that all these planets share, and it's the value of this ratio. There might be something interesting here. And it's worth expressing this in perhaps a different way. So remember that we can write the period of a planet, a planet's orbit. The sidereal period can be related to, let me imagine that we're only doing circular orbits, so R and A are the same thing, and I'll call A R. And so I can write the period, relate the period to the radius of the orbit and the speed, which I'll assume uniform because it's a circle, with which the planet orbits the sun. So the period is simply the circumference of the orbit, 2 pi r, divided by the speed with which the planet moves. So this is my expression for the period, and A is simply r in this case. So Kepler's law becomes, well, I'd have to square this thing, so 4 pi squared r squared over v squared is k times r cubed. And I have some enticing cancellations here. I can cancel r squared and leave just 1 power of r over here. And what I can find is an equation that we might find use for later that says if you know how far from the sun a planet orbits, from this you can figure out its period. From this you can figure out the speed with which it's moving, multiplying by v squared and dividing by kr. I find that v squared is 4 pi squared over kr, a relation to which we will have time to return. And what is the numerical value of k? Well, k is a kind of funny physical constant, the first of its kind, but we'll meet many of them. Remember that a is a length in meters or astronomical units or whatever it is. P is a length of time, so k is some number of perhaps seconds squared per meters cubed. It is a completely different number of hours squared per mile cubed. K is a physical constant which depends on the units you're using. You can always pick your units of distance and time to make k equal to 1 if you so desire. In natural units that we will try to use, seconds and meters, it most certainly is not 1. But the important thing for us is that k, whatever it is the same for all the planets. And that is hinting at some deep underlying physics because it's something that is true for all of them. Setting this aside for a minute, we have other progress. Galileo, about a year after Kepler obtains his laws, gets his hands on the newest technology, a telescope, a spyglass. And we don't know if he's the first to do it, but he was certainly the first to publish this and to become known for it. He used a telescope to look up in the sky. And he finds many, 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 many exciting things when he looks up at the sky with this newfangled invention. The first thing he finds is that Venus, the planet Venus, goes through phases, which is not surprising to us. It's a chunk of rock. It's illuminated by the sun. Its angle to the sun changes. So Venus goes through phases, but in particular, the relation between the phases of Venus and its position in the sky show that sometimes Venus is closer to Earth than the sun is, and we get effectively a new Venus just like the new moon works. But on the other hand, unlike the full moon, which happens when the moon is on the other side of Earth from the sun, Venus is never that 12 hours away from the sun in right ascension. Venus is always near the sun, remember. A full Venus happens when Venus is on the other side of the sun from Earth. And what this means is this does not fit in with the precise parameters of the Ptolemaic model, but it fits very nicely into the Keplerian or even the Copernican model. Also, he discovers that Jupiter has satellites. He sees the 4 Galilean moons, or as he, seeking patronage, calls them, the Medicean stars, moving back and forth around the image of Jupiter, and he realizes quickly that what he's seeing is something, a collection of bodies orbiting Jupiter. Well, they're clearly not orbiting the Earth, so this is an important piece of breaking down the cultural objection to the Earth moving. He sees various exciting things. He sees mountains on the moon. He sees sunspots on the sun. He sees some weird structure on Saturn that later Huygens discovers are the rings of Saturn. So Galileo finds many things with his telescope, and in particular, the evidence of the phases of Venus is really the smoking gun that dooms the geocentric picture, or the Ptolemaic geocentric picture, as we will talk about later. Whether you think that the Earth is stationary and the whole universe is doing a complicated motion or something else, at the end of the day, that's a very difficult and almost philosophical question. We'll see what we can have to say about why we prefer one description over the other, but in particular, the fact that Venus is sometimes behind the sun and sometimes in front of the sun, that's now a fact. And this does not fit with the Ptolemaic model. Galileo also applied himself to beginnings of the science of mechanics, the study of motion, and is well known for formulating what is called the principle of inertia. As he put it, an object will retain its state of motion unless disturbed externally. Now, we are all familiar with this in the following painful sense. If you have a refrigerator that's not moving, and you want to set it in motion, you want to change its state of motion from rest to motion, you have to expend quite a bit of effort to move that refrigerator. What Galileo reminds us is, but then if you let it go, the refrigerator will stop. What Galileo realized is that this is an artifact of rubbing against the floor. And if you put the refrigerator on ice or on roller skates and started it moving, it would be just as hard to stop it or change its direction of motion as it was to get it started in the first place. And that is an abstraction that is cannot be understated. Galileo made many brilliant deductions, but he never really got mechanics right. What was missing for Galileo, among many things, but the technical ingredient that was missing was that the mathematics required to discuss mechanics correctly hadn't been invented yet. Real progress awaited Isaac Newton, and Newton also didn't find the right mathematics. It hadn't been invented yet, so Newton just went ahead and invented it. That was the calculus, and we will have to work around it because we don't use calculus. So we've made incredible progress. Look, the planets have, and in general, the heavens have been removed from some spiritual realm of spheres, and we now have objects that are a given distance and a given position in the universe. It's a 3D world out there. There are moons that orbit the planets. This is all a physical system. We can study it, we can observe it. Galileo observes the moon as a moon, something to be observed, not some heavenly object. We have Kepler's laws, and the predictions of Kepler's laws from such simplicity, such precision, is extremely compelling. Moreover, it turns out that these laws are a lot more universal than Kepler could have imagined. In fact, they govern any kind of orbiting system. They govern the solar system. They govern the various moons of Jupiter, as was discovered not long after he published his book. They govern every orbiting system, in some sense, electrons in an atom. Each system is characterized perhaps by a different Kepler constant K. That was a property of our solar system. But the relation, the fact that the orbits are ellipses, and the central object is at one of the focal points, and that the semi-major axes and the periods are related by p squared equals a constant times a cubed for different electrons orbiting a nucleus or different moons orbiting the same planet. This, it turns out, goes way beyond what Kepler put into his model, comes out of it. And in physics, when something is that universal, it tells you that there's some fundamental law underlying it. There's a reason why all of these things share a behavior. And again, these underlying physical laws, of which Kepler was just finding the manifestation in the solar system, were awaiting discovery by Newton. So we're now ready to discuss Sir Isaac.